Eccoci qua. So let me start from the last formula that we derived. We said that the logarithm of the grand canonical partition function. Well, doing a little bit of algebra, then it was E beta mu G. Well, actually, no, I didn't put any degeneracy actually. So it's V, and then there is 1 over lambda cubed, see, and then 1 minus 1 divided by 6, then Q H bar 2 MC squared B divided by KBT squared. Yeah, I think that we arrived at this point. So I just wanted to remind you what was the idea of this calculation. It has to do with the quantization of the trajectories, if you want, in the plane when dealing with gas of particles in a magnetic field. And so basically in the z direction, well, the momentum is provided by the usual formula, whereas in the plane, somehow you split the motion into an harmonicals, into if you want, a superposition of a harmonic oscillator, and you just change the centers of these oscillations. When you change the centers of this oscillation, it's basically a kind of degeneracy, which is related, is proportional to the momentum direction x. And then you have a quantization of the levels as the typical, by using the usual formula for harmonic oscillators. Okay? This quantization of the levels is called Landau. So these levels are called actually Landau levels. Okay? And yeah, then after that, we somehow counting the number of states, we have computed the grand canonical partition function. Then we have done a classical limit, not because we are lazy, just because it's easier to do the calculation. Actually, one can also study the same problem at t equals 0, and then actually my previous idea was to study also that limit, but it's much more complicated. I have the notes, but and there's no time to do it. Okay, so we will study just the high temperature limit, which was this limit that's been derived in the case in which the temperature is high. Okay, good. So yeah, so then I think we arrived at this point, and yeah, so I think that I was about to say that this is basically just the number of particles, this guy here, because let me see, so mu is kBt, the log of n lambda cubed, the classical, and we are in the classical limit, so the fugacity approaching 0. From this mu, beta mu is the log of n lambda cubed, therefore this is just n lambda cubed times the volume divided by lambda cubed. This lambda goes away, then n times b is n. So basically the log of the partition function, grand canonical, is n, so the number of particles. Then I have 1 minus 1/6. And let me introduce a quantity which is Q H bar divided by 2 MC. And since you are young, you might remember which is the name of this quantity. No. Exactly. Il magnetone di Bohr, or and so let me introduce this quantity. So at the end it is 1/6, and then I have the mu 0 squared mu0 squared, and then B divided by KBT squared. Ooh. Yeah, so, okay, of course, when B is equal to 0, we discover again that the log of the grand canonical partition function is n, which is correct, and so this is a good check to do it. And then there is the first order correction in B. Well, actually, one should say better, mu0 B divided by KBT must be small, okay? So when talking about something which is small, of course, or something that is large, of course, one has to compare with another quantity. So in this case, what we are saying basically is the correction to the classical case, so to the case in which there's no magnetic field, is a mu0 BKBT correction squared, right? So this quantity here, mu0 divided by KBT, if you had done the calculation correctly, must have the dimension of a magnetic field. Yeah, so anyway, apart from that, now we said that the magnetization is KBT times the derivative with respect to the magnetic field of the log of side of G. And so now I just need to compute this derivative. And now the first term does not get any contribution from me. I just have the second one, which is then 1/3 minus 1/3 mu0 squared B divided by KBT squared. Okay. There is something that I'm forgetting. Yeah, there is a KBT there, so that this goes away. So in principle, it should be just minus 1/3, and there is a n, of course. N, sorry, it's morning. C'è la n, il b misura t. Okay, good. So our effort was to compute basically now this quantity, which is the magnetization. You can notice the sign that is opposite to the magnetic field. And also, if you compute the isothermal susceptibility, which was the derivative of the magnetization with respect to the magnetic field. Now this is computed at fixed temperature and actually also fixed volume and fixed chemical potential. We are in the grand canonical ensemble. Yeah, so then this is just minus 1/3 mu0 squared n divided by KBT. KBT, okay. So now, of course, the most interesting thing about this diamagnetism, well, when we say it's the diamagnetic, well, because basically, because of this minus, okay? So now if you switch on the magnetic field, you see that the magnetization has just the opposite sign as the magnetic field. And also well, the same is clear from this. So this is a constant and it is independent from the magnetic field, at least at this order, okay? So the fact that you have a minus here, the diamagnetic. When the susceptibility is smaller than 0, we say that the material is diamagnetic. Okay. Now, so we have done the calculation for charges. We did not specify which is the nature of those charges. They could be electrons, for instance. But so our first comment is the following. In general, those charges, if you think about electrons, okay, of course they feed the Lorentz force, but there is another thing that one should include in principle when dealing with the magnetic field, which is the coupling between the intrinsic magnetic moment of the electron and the external magnetic field. So actually, if you do the calculation by including this effect, which is the quantization of the trajectories, and the effect of the coupling of the intrinsic magnetic field, well, the intrinsic magnetic moment and the external magnetic field, then actually you see that in total, if for a gas of electrons, actually paramagnetism will dominate, not diamagnetism. But there are some materials in which actually this is the dominant effect, okay, although it's a small effect. What is interesting, what I find interesting also that this is a quantum effect that survives even a large temperature, okay, so this is always something that one has to remember. We have a limit, which is the classical limit, but so for an ensemble of particles, okay? So we have many particles, and nevertheless, we see something that survives from quantum mechanics and actually provides a measurable effect. Indeed, again to this point, if you treat the problem classically, there is no such effect. In classical statistical physics, statistical mechanics. This is called Bohr van Leuven. I don't know how to pronounce it, honestly. It must be some Leuven, yeah, theorem. Let's say that classically there is no diamagnetism. Actually, even paramagnetism and ferromagnetism are not, to some extent, they are not classical in the sense that when I will talk later on about the spin and I explain the paramagnetism and the ferromagnetism in terms of spin and intrinsic magnetic moment, of course, this is also non-classical effect. But talking about instead a purely an effect which is related purely to the trajectories, usually it's about the magnetism. Okay, so when excluding the possibility of having intrinsic magnetic moment, so let's stick to this. And the reason is the following: if you do the calculations of a grand canonical, well, if you do the calculations, yeah, the grand canonical ensemble or even the canonical ensemble, at some point you need to compute the partition function. Suppose that I want to compute the canonical partition function, which at the end will enter also the grand canonical partition function. Then at some point we need to do for a single particle, and then we take this quantity to the power of n for n particles because those particles are independent. Here I will have to do an integral over dr and dp of the Hamiltonian, which is e to the minus beta p minus qcd squared. Okay, there is a 1 divided by 2n. And so you see here that so this is A, of course, is the potential vector, sorry. You see here that you can basically just shift the momentum and define P prime is equal to P minus Q A divided by C. And of course, now if you do the Jacobian of this quantity, then you get 1, and therefore basically you do not have any contribution from this. Okay, so it will be the same. If you change just the variables, dp prime of e to the minus beta p prime squared divided by 2m. So you see that there's no effect on the magnetic field anymore or the potential vector. So the classical partition function that you compute in this case is the same as the one without the magnetic field. That's why there's no effect in the classical partition function of the magnetic field. So therefore, you cannot explain this phenomenon. Okay. Whereas when doing the calculations within quantum mechanics, we have considered this quantity to be an operator, and therefore we have also not changed. We have split the three contributions in x, y, and z, and we put dots these harmonic oscillators with the quantized levels. Okay. So in this respect, this effect is explainable only in the context of quantum mechanics and statistical physics with quantum mechanics. So before proceeding, let me just propose you an exercise. I think it's a long time I don't do it. So if you want just to try to do it, it's up to you. And then we move to critical phenomena. So this is an exercise which deals again with the ground canonical and fermions. And let me see. It's an effect which is called thermo-ionic effect, which is the effect of well, basically when you heat up a metal, you release electrons. Okay, so this exercise you can compute, which is the current, the charge current that you have when you heat up a metal and you release those particles, those charged particles. Okay, because of the fact that you are increasing the temperature. The model is done in the following way. So first of all, let's consider here the energy of the electrons. And okay, this is a picture that is typical from solid state physics, so that you might have seen before. Suppose that we are t equals 0, and we have the electrons sitting, occupying all the levels up to the Fermi energy. Okay, so these are all occupied levels. And suppose that t equals 0 to make it easier. And there is basically this Fermi C is below the energy level equals 0 because they are bound. And there is an energy gap which is called work function indicated by W. W is the work function, which is the energy that you need to provide to an electron sitting exactly on the Fermi surface in order to be unbound. Okay? So this is the energy to unbound an electron. Unbound, unbind. Unbound is unbind. Bene. So basically, what you need to do is to have an energy, a kinetic energy of the electrons, the component orthogonal to your plane. So suppose that you have a plane here, which is, let me see, I put x, for some reason I put here the x-axis. Let me see, this is y, and this is z. And so here you have the electrons in this plane, this sheet of metal. And you want to ask, so the effect is due to the fact that the component of the kinetic energy in the x direction, so 1 mvx squared, is larger than than the work function, basically. Okay. So what you do is to consider in this calculation that I will now just sketch that the energy. So let's say basically the thing is that to count the number of electrons with energies which are larger than EF plus W. So you take all the possible electrons from below. So a number of electrons with energies which is larger than EF plus W. And so to do the calculation, so then you introduce a current. Of course, I will not ask you these are the exam. It's just an exercise if you want to try to do it. This is the thermoionic current, which is the charge of the electron times the density times the average component in the x direction of the velocity. Okay, so this is the density step. And so basically the thing is to compute the right number of electrons that they can jump outside the material, which is basically compute this average velocity, dx, that you write in terms of 1 divided by n, and just a normalization, n is the total number of electrons. Then you have, okay, so here you have the standard normalization, so volume 2 pi h bar cubed. Let me put a degeneracy here, G is 2 for electrons. This is a degeneracy. It's a spin degeneracy. And then we have the integrals. Now we can show you the design. No? dpx, dpy, dpz. Now dpy, dpz can be integrated from minus infinity to plus infinity. I do not have any constraint on these components of the momentum. Whereas on the x, I have the constraint that, okay, plus infinity here, and here I have a minimum of x component, which is basically, which comes basically from the requirement that the energy is larger than this, than EF plus W. I will write it in a moment. Now here you have to put, I'm computing the average velocity, so I need to take the function, which is the velocity in the x direction, which is px divided by m. And of course, now I have the occupation number, which in a Fermi-Dirac will be, so this is px divided by m, is 1 plus e to beta. So here I have the typical epsilon p minus mu, where epsilon p, of course, contains all the terms, all the three contributions to the kinetic energy that we call ex, x component, if you want. Well, it's really useful to do that. Facciamo senza complicarci la vita. Facciamolo così: px squared divided by 2n plus py squared divided by 2n plus pz squared divided by 2n. Okay, so this will be basically just Vx. Then you have, just to compute this integral, well, this is the correct expression. Here you have Fermi-Dirac. Of course, this is a pain to compute the integral with the Fermi-Dirac. So typically what you do is to imagine that this can be approximated by, so let me see, E p minus mu. You do the classical limit, which is E beta mu, which is an external multiplicative factor, times e to the minus epsilon q epsilon p beta. Is it really possible to do this limit? Well, basically, we say that Ex, which is Ex squared divided by 2m minus mu must be larger than W in order to have unbind the electrons. So the energy must be larger than the Fermi energy plus the work function. If, what is if V is much larger than KBT, then we can say that also Ex minus mu is much larger than KBT. And therefore, we can assume that basically this function here dominates over the temperature, over the KBT, and we can approximate to a Maxwell. But this, honestly, is just to do a simple calculation. One in principle should consider just this, because electrons are typically degenerate in metals. Okay, so if you do this and you do the calculations, you basically just need to compute now this integral. So the Vx average is 1 divided by n, volume degeneracy 2p h bar cubed. Then you have dpx, dpy, and dpz. Cancelliamo. This from minus infinity to plus infinity, minus infinity to plus infinity. Here I have a minimum of momentum in the x direction. And here then I have px divided by m, e beta mu, and then I have e to the minus px squared divided by 2m beta, e to the minus py squared divided by 2m beta, and e to the minus pz squared divided by 2m beta. And I think I have everything there. So tutto, sì. Okay, so now these integrals in pz and py can be done as usual as Gaussian integrals, and they will provide basically a factor of lambda, okay, of thermal wavelengths, inverse thermal wavelengths. Then what is left is this integral here, which is the only difference with respect to the typical case, in which you have this, which is px divided by m, and exponential of px squared beta divided by 2m, where this px minimum is provided by the condition that that you have a kinetic energy which is larger than which is larger than what we said before. So Px squared divided by 2m larger than mu plus or mu or Ef are the same plus W. Okay, this provides the minimum of this quantity. So now the calculation proceed. I will not do it because this is an exercise. And if you go on and try to do the calculations, so you just have these integrals to compute, at the end you get a formula that tells you that the current, the thermoionic current, Gx, for the case in which G is equal to 2, the degeneracy is equal to 2, it's 4 pi En, where En is charge of the electrons time. Sorry, no, this is not N, but this is M actually. Sorry. The N cancelled at some point. Yeah, the N cancelled because there was a N, there was a V at the numerator, there was a V divided by N, that's why I have not that in there. So this 4 pi EM, then I have H cubed, not H bar, but H, KBT squared, and then I have the exponential of the work function. And this is called the Richardson Duchamp, the near know how to pronounce. Duchamp. No, Dushman. That provides you a formula once you fix the temperature to obtain the current due to the fact that you are heating up the material. Okay, this is just if you want to try to make some exercise in this. Okay. Of course, now you see that in this formula, as usual, since you have an energy gap, whenever you have an energy gap, is a general comment, there will be an exponential suppression, which is provided by e to the minus the size of the energy gap divided by kBt. This is the classical exponential suppression that you have always when you have energy gaps or discretizational levels. So this one could expect that you have this factor this exponential suppression. The thing of statistical mechanics basically is to provide a way to compute the prefactors typically. Okay, in this case, it's a quadratic dependence on the temperature. And of course, the prefactor could be very important in the sense that they can change significantly the temperature for which you need to have you start to see some effect. And typically, you don't need to reach really the energy of the energy gap. So to have kBt is equal to this, because that would imply very large temperature. But because of the prefactor, you start to see some effect also before. I think I have commented this also in the case of ionization, so this is a similar situation. Okay, so now we move to the last topic. Well, not really the last, it's almost the last, in the sense that in the last 2 hours, I think I will try to do some dynamics, maybe, if I manage, but I'm not sure. I would like to talk about the Brownian motion and random walk and stuff like that, at least in the last 2 hours. Of course, in any course of statistical mechanics, at some point one should see at least the word physical phenomena, and we have to say something about that. Now, in the past, and I hope that in the future there will be again a course on critical phenomena by Zivieri. I don't know if any of you, qualcuno di voi aveva seguito il corso per caso? C'è qualche veterano che ha seguito il corso di Zivieri di fenomeni critici? Forse no, non so.
No.
Okay, so in the past there was this course. Now this year it's not there anymore. And actually the subject here would deserve really another course because it's long and quite complicated, especially when dealing with renormalization. So what I will do is just to present some arguments in this topic, just to provide you some feeling about what happens when you have a system at the critical temperature and what is happening there. What is interesting this kind of physics? The interesting part is that it's universal in the sense that you can have many different types of systems with different microscopic interactions, different properties that behave in exactly the same way, close to the critical point. Okay, so there is a thing called universality that tells you that a certain class of models, they behave exactly the same way when you are close to the critical point, which is the point of critical temperature. So in the case of liquid gas phase transition, the critical point was this point here. Was the was the temperature T equal to Tc. This is the Pc critical pressure, and this is Vc. And it is exactly the point in which your feeling, if you want, about what is gas or what is liquid actually, well, if you go from below, you start to see that these two types of material are actually behaving the same way. Okay, so you cannot distinguish what is the liquid and what is the gas. Okay. Or if you go to from above, from T larger than Tc, below this point you will start to see the separation of gas and liquid, because below this point you start to see the mixed phase, right? So you have the phase separation. Also, okay, but here exactly at this point is the point in which, if you want, then after that, below that point, phases start to split. Or if you go from here to here, the two phases are actually behaving in exactly the same way. And we already commented on the fact that here your thermodynamical variables could have some singularity due to the thermodynamical limit, but they will have some singularity, and we will actually, well, all the study about the critical phenomena basically is about studying the system close to this point, and how the thermodynamical quantities behave close to this point, and if some of them diverges, to study how it diverges. And basically, there is a thing called universality. Okay, maybe we will see later. I'm not sure that we will have enough time. Sorry for asking you again questions about what you have seen in the past, but it's. Aspetta, ve lo chiedo in italiano. Qualcuno di voi ha già seguito il corso di sistemi complessi? Anche quello è un corso opzionale, quindi non assumo che lo abbiate seguito tutti, ovviamente, quindi sì o no innanzitutto?
Io no.
Io no.
Ok. Quelli che l'hanno seguito hanno già visto, immagino, però io chiaramente lo faccio per tutti perché fa parte del background generale, il modello di Ising o di Ising, se lo dico in inglese.
Sì, l'abbiamo visto.
Ok, questo l'avete visto in una dimensione, in due dimensioni, in generale, in che tipo di sistemi?
In una dimensione abbiamo calcolato la soluzione esatta,
Quella si calcola esattamente.
in due abbiamo fatto i risultati.
In due risultati non avete fatto il campo medio?
Ok, sì, abbiamo fatto campo medio. Sì, non la soluzione esatta in 2D, quella no.
Certo, in 2D è un casino, sì. Okay, so now concerning this part, so for those of you who have already seen this, you might also disconnect in the sense that um, I think that so the thing is the following, that when dealing with critical phenomena, of course, the Ising model has a special role in the sense that it is a model simple enough to understand a complicated behavior. And at least in one case, one can do, well, in two cases, one can do analytical calculations. The two-dimensional case is completely out of my target. It's a very long and complicated calculation. So, but we have the exact solution by Onsager. I will do the 1D calculation, which is done analytically, and also the 2D. Well, actually, in general number of dimension, one can do it in mean field. The word mean field is also something that one has to know. It's part of the background, okay? So I think it's important that I do it, even though some of you have already followed the course on complex systems. It's something that I have to do for the others, okay? Now, maybe if there is enough time, but I'm not sure, I will say something the Landau-Ginzburg approach to the critical phenomena, and I don't know if this was already also covered in the case of complex system, of the lab of complex systems. I'm not sure, but
Sì, abbiamo visto anche quello.
okay. So, because I think that maybe for the next year, I should somehow, so this is the first year that I will do statistical physics. For the next years, maybe I need to somehow manage with Tripiccione in order that we have less overlap, in the sense that there are some things that I need to do here that are almost necessary, that he can avoid to repeat, basically, because this is a course that is mandatory for all of you, whereas the lab of complex systems is an optional course. So, okay, so this overlap is unavoidable this year, and we will try to solve this problem the next year, but it's mainly a problem of not of this course, but of the other one, because in this case, I think I need to do those calculations. So in any case, so for those of you who have seen already the Ising model, you can also, you can go to the bar and have breakfast, and not horses to see this. Okay, so why we like to introduce the Ising model, just because it's very simple, okay? And it provides a way to do the calculations, so a way to understand which is the mechanism of critical phenomena, and more generally in the Landau-Ginzburg approach. Okay, so this class of models is really a classical of topic in statistical mechanics. Well, let me start with the 1D case. In the 1D case, we basically have a chain of spin, if you want to think about spin, that can be in two states, up and down. So we have a linear chain of spin. Okay. That are in discretized position. So in the canonical partition function that we compute, there's no volume, there's no position, there are just the states which can be 2 for each spin of these particles. Okay. Now, what is the Hamiltonian of this model? Let me write already the eigenvalue in the sense that it's the eigenvalue of the Hamiltonian once I project over the spin, and will be something like that. So suppose that I have n particles, and the first term is the mutual interaction of spin, that's called sk plus 1, where sk is the spin of particle k, and sk can have 2 values, can be -1 or 1. So each of these spin can have a -1 or +1. And so this is the term, which is a mutual interaction between spin. And what says this term? That if they have the same one, so if it is 1 times 1 or -1 times -1, so the same spin, you are happy in the sense that the energy has a minus there. So you minimize the energy when 2 spins that are close by, the nearest neighbor, sorry, you are happy in the sense that you can decrease the value of the energy, and there is a coupling here, which is epsilon. So it's a coupling constant if you want. The larger the coupling constants, the more the happier you are when 2 spins are pointing in the same direction. And of course, there is the possibility to include the interaction of spins with an external field, which is called H, external magnetic field, and is 1 and is just SK, where H is an external magnetic field. Okay. I think that the systems of spin is very useful in statistical mechanics, and we have seen this already when introducing statistical mechanics, just without this term. We start everything by saying, okay, if I have a certain number of spins, which is the probability that the total magnetization is 0, and I say, of course, this is the most probable value, and we have computed also the dispersion. We found a Gaussian relation. Now, what we are introducing beyond that is the interaction between the spins. Okay. Now, this is a linear chain that, of course, will have some boundary effect in the sense that at some point you don't like too much this in the sense that the first one couples with the second, but there's no previous one to which you can couple, and the same is for the last one, no? So actually, this formula written in this form is actually not correct in the sense at some point I will go to Sn plus 1, and actually one introduced what is called periodic boundary condition, which is the following. That Sn plus 1 is equal to S1. So basically, it's just like having a kind of circle of spins. This is 1, this is 2, etc. up to n, and then you go back to 1. Okay. So we introduce this periodic boundary condition which Sn plus 1 is equal to S1. Good. So now what we do, we have the Hamiltonian. So here is a, if you want, is a classical Hamiltonian, or is the eigenvalue of the Hamiltonian already. Okay. When projected over a set of spins, of state of spins, and we can compute the canonical partition function as follows. I'm going to put it more like one. Now I will write first, and then I will comment this sum over S1, sum over S2, sum over Sn of E. Here you have minus beta energy, so it's beta which multiplies epsilon times the coupling, which is the sum over k to 1 to n of sk plus 1. And I have here plus h sk h plus sk. Let me put this here so this is better. And yeah, the sum actually is over epsilon sk plus 1 plus h sk. Okay? Where here I'm summing over all the possible values of S1 and S2 and Sn, which can be minus 1, 1, minus 1, 1, etc. minus 1, 1. Now, is this somehow weird? Well, actually, it has the form of a trace in the sense that this can be thought as e to the minus beta times the Hamiltonian. Let me say m just to not to confuse with this, which is a magnetic field. The Hamiltonian contains, instead of the eigenvalues, it contains the operators, which can be sigma 3, for instance. And when doing the canonical partition function, I should sandwich this operator in all the states S1, Sn, and sum over the two possible eigenvalues of S1 and Sn. So that's why what I wrote there is already if you want, the trace of this operator. Okay. Good. So the next step is to write in a slightly different way the sum. So let me put sum S1 Sn, just to avoid to write so many sums. This is E beta. Here you have the sum from K1 to N of epsilon sk plus 1 plus, here I put H times sk plus 1. This is divided by 2. Why I'm doing that? Because for instance, if you take s equal 2, I get two contributions. So from this term, so suppose that I have the first term will be like S1 plus S2 divided by 2, plus then I have S2 plus S3 divided by 2. So the S2 and S2 gets two contributions, one half S2, one half S2, which is S2, which is is correct. And for the border, I get here S1 plus 2, and at the end I will have an Sn plus Sn plus 1 divided by 2, but Sn plus 1 divided by 2 is equal to S1 divided by 2 because of the boundary conditions, and so therefore I will just have an S1, okay? So the boundary condition allows me to write this term as sk plus 1 divided by 2. Okay. Now, typically one does here a trick, which is a very nice trick, which is the following. Well, actually, as I said before, what I'm writing there is already the trace of the e to the minus beta times the Hamiltonian. But let me introduce a matrix which we call P, the standard notation of the Kershaw-Wang, which is S P S prime, which is basically e to the minus beta times the Hamiltonian. Well, not really the original Hamiltonian, but this one. Okay. So let me consider the case in which I project this. Let me write it explicitly, actually. So let's write P as e to the beta times epsilon s prime plus h s plus s prime divided by 2. Okay, let me write this in terms of this operator. And now, let us compute the matrix. Let us compute the matrix element. So I will have P1, 1, P1, meglio dire 1, 1, sorry, this is 1, 1, so this is 1, minus 1, P1, 1, P minus 1, minus 1, P minus 1. Which are the possible states of the two S and S prime. Okay, so for 1, 1, I get exponential of beta times epsilon plus h. Because here you have 1, 1 divided by 2. Similarly, in this minus 1, I get an exponential of beta, here I have my epsilon minus h, because I have minus 1, which is minus 2 divided by 2 is minus 1. And in the other case, I get that this component goes to 0 because I have a plus 1 and a minus 1, and I just have this term here, which is e to the minus beta epsilon, and here is e to the minus beta epsilon. Okay? So basically, the matrix form of this P is E beta epsilon plus H, E beta epsilon minus H, E to the minus beta epsilon, E to the minus beta epsilon. Okay. Now you will see in a moment why it is useful to introduce this matrix. Which I can cover quick. And let me start again with the canonical partition function, which was the sum S1 up to Sn of e to the beta. Let's write explicitly which are the terms of this sum. So here I will have epsilon S1, S2 plus h divided by 2 and S1 plus S2. This is for 1, 2. Then I will have S1 più S2, sì. Epsilon S2, S3 plus H S2 plus S3 divided by 2, plus all the other terms. Okay? Now, basically what you have there, so consider just the first one. Consider just the first, so these are actually the product of many exponentials. Consider just the first one. So it's beta S1, S2 plus H divided by 2 and S1 plus S2. Then there are all the other exponential, okay? If you just take the first one, this is basically the operator P or the matrix P with sandwich S1, S2. Okay? Because it has this form, instead of S prime, you have S1, S2. Similarly, for the second, you will get the second exponential is a sandwich between S2, P, S3, etc. So all of them are actually matrix element, and actually they are even summing over them. So Z of C is the sum S1, S2, Sn of the first sandwich, which is S1P S2, then I have S2P S3 up to the last one will be SNP. Here I should put Sn plus 1, which is S1, by choosing our boundary condition. Okay. Now, here I'm summing over S1, S2 up to Sn. When I do the sum over S2 of S1, P, S2, S2, P, S3, is actually like making a product, which is the product of two matrices, right? So this is basically just the P squared S1, S3 component, no? Because it's like making a product of two matrices, prodotto di Capolomma, okay? Where I'm summing over S2, and this is the S1, S3 component of the matrix P squared, okay? And of course, the same will be when considering all the other terms, okay? So at the end, you get many so basically the sum is just a product of P by itself many times, n times, and at the end sum over S1. Okay, so at the end you can write the canonical partition function is the sum over S1, which is left from here. And yeah, all these terms basically are matrix. The matrix is always the matrix P, which will be to the power of n. So S1, P, and S1. Okay, so this is the trick to see all of these products as actually the product of P by itself. Now, what is written here, S1, let me be more explicit, from -1 to 1, is actually the trace of the matrix Pn. Okay? Because I'm summing over, I'm doing the sandwich on the same states, and I'm summing over the states. And the trace of Pn can be written if I diagonalize P, okay, suppose that I can write a basis, I can find a basis in which P is diagonal, and it will have the form of lambda plus lambda minus 0, 0. The trace does not depend on unitary transformation that I can operate on my operator. So therefore, I'm sure that I can compute the trace of this matrix in a base in which the matrix P is diagonal, and if this is diagonal, P to the power of n is just lambda plus to the power of n, and lambda minus to the power of n, and then the trace is just the sum of these two eigenvalues to the power of n. This is lambda plus to the power of n and lambda minus to the power of n. Okay. It's very elegant indeed. It's very elegant, and now what is needed is just to compute the eigenvalues of the matrix P. The matrix P, it has a form that we derived before. Dov'è che stava? Eccola là. And now if I want to compute the eigenvalues, I just need to write the second equation. No? So the matrix P has this shape. P is equal to E beta epsilon plus H e to the minus beta epsilon, e to the minus beta epsilon, and exponential of beta epsilon minus H. And in order to compute the eigenvalues, I just need to solve and write and solve the equation, which is E beta epsilon H minus lambda times this guy beta epsilon, sorry, this is a plus H, this is a minus H, minus lambda, minus, diciamo questo, yeah, minus E to the minus 2 beta epsilon equal to 0. Che sono? Sono le 10 meno 4. Now, okay, I can solve this equation. Maybe I will avoid to do all the mathematical details. Only just solve now this equation, and you will find solve it, and you see that the two eigenvalues, the lambda plus or lambda minus, are provided by E beta epsilon hyperbolic cosine of beta H, and then there is a plus minus the square root of E ma quasi quasi le salto un passaggio. No, vabbè, dai. Okay, you have plus minus the square root of 2 beta epsilon whole square beta H minus 2 sen H of 2 beta epsilon. Questo è così. Okay, now I will jump a little bit. And you find that the lambda plus minus, you can collect E beta epsilon outside. Then you have the cos, hyperbolic cos of beta H plus minus. And here we have sen H squared beta H plus 4, sorry, plus E to the minus 4 beta epsilon. Let me close this. So those are the two eigenvalues of P. Now the trace, so the Z of C, it was the trace which was lambda plus to the power of n plus lambda minus to the power of n, which is equal, almost equal to lambda plus to the power of n, because n is very large, and lambda minus is smaller than lambda plus because it has a minus here. Okay, so I can neglect the contribution from the smallest of the two eigenvalues because they are to the power of n, and therefore the canonical partition function is just lambda plus to the power of n. So then I can conclude that Z of C, since I have the formula for lambda plus to the power of n, is just e to the beta epsilon n, which comes from this. Then I have the cos, hyperbolic cos of beta h plus square root of sinus squared h of beta h plus exponential of minus 4 epsilon beta, and this always to the power of n, again to the power of n. Okay. Now this is the canonical partition function. Now we know that the canonical partition function allows me to find the Gibbs free, the Helmholtz free energy, which is A, which is minus kBt, the log of this quantity, minus kBt, the log of this quantity. Okay? And so I have all my thermodynamics now fixed, and if you want, I can write that A divided by n is equal to minus epsilon, just by computing the log of this quantity here, multiplied by minus kBt, and I get a minus epsilon minus kBt, and then I have a logarithm of the cos beta h plus sinus squared h beta h plus e to the minus 4 beta epsilon, and that's it. And the n is here. Okay. Now what we do next, this is the energy, the Helmholtz free energy per particle. Of course, I can compute all my thermodynamics out of that, and actually, I think at some point I will compute, or at least I will sketch the computation of the internal energy and the specific heat. But let me now, first of all, compute the most important quantity in this context, which is the magnetization again. And what is the magnetization? So we come back also to the problem of last time. Now, this is defined as the average, the ensemble average of what? Of the sum from k1 to n of sk. Okay, so I take all the spins, I sum of them, and then I average over the ensemble, over the canonical ensemble in this case. Okay. Now, this quantity here, you can convince yourself, but I will show it, that is actually kBt times the derivative with respect to h of the log of Z of C, which is indeed very similar, well, actually is the same as the formula that we wrote last time, that was kBt for the Landau derivative with respect to b. I'm sorry, the notation is slightly different. And here I have the log of z of the grand canonical partition function, similar now the magnetism. Okay, now where does this come from? Well, you might, so you actually, you have noticed that when I take the canonical partition function, or the grand canonical partition function, I compute the log, and then when I compute the derivatives, basically those derivatives to some quantities, in the case of the internal energy, I have to derive with respect to beta. In the case of the magnetization, I will derive with respect to H. And the structure, because the structure is basically the same. So if I want to compute the internal energy, U, consider that in the ensemble, the energy is coupled to beta in the following fashion, right? So I have in the ensemble e to the minus e beta. And when I want to compute u, I need to compute the derivative with respect to beta of the log of the canonical partition function, or the non-canonical partition function. And then I have a minus there. If you want to compute the magnetization, now in the Lagrange, in the ensemble, the magnetization will be coupled to the magnetic field, actually this time with a plus, and okay, there is a beta also, of course. And so then if I want to derive the average of M, so here I want to derive the average of E, which is the internal energy. If here I want to derive, if I want to find the average of M, I have to derive with respect to H. Okay, so the structure is similar. And indeed, if you take the Z of C, okay, this was the sum S1, Sn of exponential of beta, and what do I have here? Here you have the sum from k1 to n of sk plus 1. Let me close this, and then I have the exponential of beta h, and here is the trick, sum k1 to n of sk. Okay. I'm running back again the canonical partition function as in the beginning. Now, if you derive this quantity, well, actually the log, if you take the log of Z of C, which is done for normalization, and you derive by H, you derive with respect to H, you get 1 over Z of C. And when you do the derivative with respect to H, you get the same structure as 1 as n of E beta blah blah, E beta blah blah, so the same really structure, times beta sum from k1 to n of sk. Okay? And of course, now you put this beta, which is 1 divided by kBt, you put it there, and you see that kBt derivative with respect to h of the log of the canonical partition function is 1 divided by z of c, the sum s1 sn, e to the beta, all these terms, the Hamiltonian basically, times the observable, if you want to average on, or the observable, sorry, for which you want to compute the average, the ensemble average. Okay? So the structure is always the same. So here you have 1 divided by Z of C, which is the normalization. Here you have the operator here that you want to compute, for which you want to compute the ensemble, or the quantity for which you want to compute the ensemble average. and times e to the beta h, okay, and so on. Okay, so if you want this structure here as the form of trace of the ensemble or the density matrix, if you want, O. Okay, you take the O, the operator, and you trace over the product. You trace the product rho O by rho is the density matrix, if you want. Okay. Dov'è che siamo arrivati? Okay, so this was for the magnetization. Now, once we realize that we can compute the magnetization just by doing a derivative of the log of the canonical partition function, we can indeed compute it. And so first of all, so M is, as I said before, is KBT derivative with respect to H of the log of Z of C, which is also equal to KBT derivative with respect to H. The log of Z of C is just minus beta A, and so this is minus derivative with respect to H of the A of the Helmholtz free energy. And now it's useful to compute M divided by N, so normalize with respect to the number of particles, which will be minus 1 M derivative of, well, once you can say is minus derivative with respect to H of A divided by N. That was computed before, no? We have a formula for that, and we can just compute the derivative. I put the result, some of part of the result here. When I compute the derivative by using the formula for A divided by N that we derived before, we get the denominator cos H beta H plus here we have a sinus H squared beta H plus exponential of minus 4 beta epsilon. And here you have a KBT, andiamo gesso. Then I have a beta sinus H beta H plus, here I have the square root of the denominator, which is sinus squared beta H plus e to the minus 4 beta epsilon. I'm just computing the derivative. And here the numerator I have 2, the sinus H of beta H, and the cos beta H times beta. And I close here. Good. Now you do a little calculation, so you put this here, and you will realize that actually the denominator actually drops, or part of the denominator drops. Vediamo com'è che si fa sta roba. Yeah, so you get here another factor, which is the square root, and here this term cancelled. And at the end, you get this nice formula, doing the algebra, which is the following: M divided by N, so which is the magnetization per particle, is it has this nice formula, which is sen H of beta H divided by the square root of sen H squared beta H, okay, plus e to the minus 4 beta epsilon. Okay, apart from the fact that it's a little bit complicated formula, but it's just a derivative of the Helmholtz free energy with respect to H. Okay. Now, this is the nice formula that we get for the magnetization in the case of the one-dimensionalized model. So let's try to make some plot of the magnetization n divided by n as a function of h of the external magnetic field. So here there is one point that you see that regardless of on the value of the temperature, which is in this beta, you always get that for h equals 0, the magnetization is 0. And this is already an important point. Okay? Then what happens is that in the limit in which you have very large values of h, you get 1 or minus 1. So let's put here h. So in the limit h going to plus infinity, I get 1, minus infinity, I get a minus 1, right? So we get something like this. This suppose that is for a certain value of temperature that I call T2. And suppose that I want to take a temperature which is smaller. We get the same, of course, asymptotic limit. Then I go through 0, and then I will approach again 1 is 1, and this is minus 1. And this is T1. Okay, so some comments. Of course, when H is very large, positive or very large negative, the magnetization per particle is 1 or minus 1, which is of course correct in the sense that I do expect indeed that when the magnetic field is so strong, all the particles will have the same direction, plus 1 or minus 1, depending on the sign of H. Now, this is already different with respect to the diamagnetism that I saw before. This is a paramagnetic substance. This is paramagnetism. Because you see that the magnetization has the same sign of H. If H is in the direction plus, let's say, all the spins will try to go in the same direction. The limit in which H is infinity, they have the same direction of H, and also in the case in which H is negative. Okay, so this is the first point. So here we have an example of paramagnetism, which is just the opposite as the one that we saw before. The other thing which is important is the following, that regardless of the value of the temperature, for all values of T, when H is equal to 0, then also the magnetization is equal to 0. They go through m equals 0 for all the cases. So this means that there is no phase transition in this case. There is no phase transition in 1D Ising model. Okay, this is an important remark. When dealing with the one-dimensional Ising model, there is no phase transition. The behavior is just, let's say, the smooth paramagnetic behavior in which if you switch on the field, then you have a certain degree of magnetization that is fully, the material is fully magnetized when H is going to infinity or minus infinity. But when H is equal to 0, then you have that the magnetization is equal to 0 regardless on the value of the temperature. And indeed, we will see a main difference now in the case, sorry, let me make some order here. In the case of two-dimensional, or actually many-dimension Ising model, we will do the calculations mid-field, however, and we will see that this is not the same. In the sense, we will find a temperature, critical temperature below which there exists a magnetization even if you don't have any external field. Okay, and this is the behavior of ferromagnetism as opposite to paramagnetism. So in the two, so when going to larger dimension, even the simple Ising model will provide actually a feature of a phase transition, critical point, and all this kind of physics. Okay. So in the one-dimensional Ising model, there's no magnetization, and actually one can put or one can include also present also an argument for which this must be the case. And the argument is the following. Let me present first this argument, which is indeed nice. And then we go on with the thermodynamics, although in this case there's not so much to say actually. Now, let's say this is a nice argument explaining the absence of phase transition in one-dimensional Ising. So the argument is the following. Suppose that we have a chain of spins which are, all of them are oriented in the same direction. Okay, so fully magnetized. And now suppose that you put somehow a separation in this chain, and you switch, and you take one of the two spins, you decide which one, or left or right, and you switch all of them to the right down, or all of them to the right left. So for instance, let's do the following. So we do the four on the left, we leave like them, like they were before, and we switch the direction of all the others. Okay? Now the question is, what happens to A? So to the Helmholtz free energy when you do such a change in your spin system. Now A is the internal energy minus Ts. So there are, and consider that in equilibrium, of course we are talking about equilibrium, you want to minimize A. Now, to minimize A, there are two ways. One is to minimize, well, they are not completely decoupled, of course, but I can follow two procedures. One has to have the smallest possible value of the internal energy, and to minimize U, U is minimal when all spins are parallel, because in this case you get all this minus epsilon contribution, and therefore this would correspond to minimization of U. So if it would be just for U, the internal energy, you always be in a situation in which the spins are aligned in one direction or the other, because you get all this minus epsilon contribution to the internal energy, which makes you happy. But actually, there is also this term, so, and therefore A can be minimized also in situation in which, here we are in the canonical ensemble, T is fixed, if you increase the entropy. So there are two ways. Either you decrease the internal energy or you increase the entropy. Now, what you can see here, and I will do the calculation in a moment, that if you go from this configuration to this configuration, you pay a small price of internal energy because you have these two pairs of spin, they are not aligned anymore. Here they were aligned, here they are not aligned anymore. So you pay a little price to the internal energy. So the internal energy of this one or this configuration will be higher with respect to this one, but you gain a lot in entropy, in the sense that the entropy of the gain, you have a certain gain of entropy in this situation that actually make a minimized in this situation rather than in this. Okay? And indeed, for without any magnetic field, the fact that the magnetization is zero means that the spins they do whatever they want, basically. Okay, you don't have any gain in Helmholtz free energy if you have them aligned or wrong or not. The magnetization equal to zero means that they are randomly, they take random values, either plus or minus, and there's no net magnetization. So why is that, as I said before? Now, which is the variation of entropy associated with this change of configuration? Now, the variation of entropy can be estimated in the following way. It's a Kb because of the dimension, and then here is the log of n minus 1, in which I have used the entropy of Boltzmann, and this log of n minus 1 means the number of ways I can put a separator here in this chain. So this n minus 1 corresponds to the number n minus 1 number of ways to separate the n spins into two groups. So I can put the separator in here, I can put it here or there. And if I have n particles, n spins, I have n minus 1 ways to do it. Therefore, I have a sort of, if you want, degeneracy in the sense that I have an increase of the entropy, which is basically due to the fact that in all the situations in which I put the separator and I switch the direction of the spins to the right, for instance, I get an increase of entropy, which is the Kb log of n minus 1. Okay. What is instead the price that I pay? So entropy is increasing. Okay, when doing from a configuration in which they are all aligned into a configuration in which there are two groups, one aligned in a certain direction and the other one aligned in the opposite direction. Which is the price that I have to pay to you in this case? It's a small price in the sense that here I'm losing a pair of aligned system, and so I'm losing a factor of minus epsilon to the energy, and I get a repulsion, if you want here, of plus epsilon, because the energy associated to this configuration will be plus epsilon. So the final internal energy will have a plus epsilon minus epsilon with respect to the previous one. So therefore, the delta U is 2 epsilon. Okay, so you see that delta U is small, is a small price, whereas delta S is large, is a large gain because it depends on n. And therefore, since you want to minimize the internal the Helmholtz free energy, when you compute the variation delta A of the Helmholtz free energy, you get a 2 epsilon, which is the variation of the internal energy, which is as a plus, minus T kb log of n minus 1, which of course will be dominated by this term. This term is leading. Okay. Now this is the explanation, the empirical explanation of the fact that it's better, we put it here, it's better to have a random direction for spins. Of course, this argument is for h equals 0. Does not hold for h finite. For h finite, we have seen already there is some degree of magnetization. But if I have the magnetic field switched off, then having a disordered configuration which they have some misalignment between the spin is good in the sense that they have a lot of gain in entropy regardless of the temperature. Here I'm not touching the temperature. Okay? So it's better to have random direction for speed at h equals 0 for every value of t. Okay? And the price to pay for the increase of u is small. So in the one-dimensional case, even if we have this coupling, minus epsilon sk plus 1, actually entropy is dominating, okay, regardless on the temperature. Now, with the one-dimensional Ising model, one can do many other calculations. Let me just mention other two calculations that I will not do explicitly because it's just a matter of for doing some algebra. Now, if you have the canonical partition function, and we have derived it exactly, you can also compute the internal energy, which will be the minus derivative with respect to beta of the log of the canonical partition function. You can do the calculation by yourself if you want to do it, and you will find that u is equal to minus epsilon n, the log, sorry, it's not the log, but the tangent, hyperbolic tangent of beta epsilon. This calculation, I've done it for u equals 0, for h equals 0. Because for h different from 0 is a little bit boring and length, so I mean it's not so useful actually. You don't gain anything new. In the sense here, what is important is to remember what I said before. The main message is the magnetization. That's the plot of the magnetization and interpretation of this result. But you can do also the thermodynamics if you want, compute for instance u, which will be provided by this formula. Now you see that when, well, let me see, when the temperature is going to 0, so let's do this limit. If t approaches 0, what happens in this is the tangent, hyperbolic tangent goes to 1, and then u approaches minus epsilon n, which is indeed the case in which all spins aligned. And actually S will be equal to zero. The entropy will be equal to zero because all of them are in the same state. If you want, you can also rephrase what I said before by saying that a phase transition actually exists only when t equals zero, which is meaningless, of course, okay? When we talk about phase transition, critical temperature, only the critical temperature is different from zero. Of course, if you go to t equals zero, the entropy is zero, as it must be, third principle of thermodynamics, they are all in the same state, and therefore the the Helmholtz free energy is just provided by U, and U is minimized by having all the speeds aligned, which is minus epsilon n. Okay, so if you want, the only situation in which they really would like to be aligned is the case in which t is equal to zero, which is of course a trivial situation. Okay. Whereas what happens when t is going to infinity? Well, in this case, u approaches zero. T going to infinity, here you have the hyperbolic tangent of zero, that is zero. And of course, in this case, actually, even if I pay price in u, in the sense that here you have the minimum value of u, here you have u equals zero, but in terms of free energy, Helmholtz free energy, here entropy is zero, so the free energy just determined by this number, whereas here the free energy gains a lot in terms of entropy. Okay, u equals zero. And in that case, of course, there's no magnetization, there's no preferred orientation. So if you want, the message of this is that for t going to zero, only in the limit t equals zero, there is a full alignment. Alignment, credo si scriva, con la G. Alignment. Okay. So this is concerning the internal energy. Then one can work out also the specific heat or the heat capacity, which is a further derivative. So if you don't have you don't have anything to do in the weekend, you can try to compute also the heat capacity, du dt. So here, just for tradition, I put the volume, but actually there's no volume here. Okay, the positions are fixed. So the volume is fixed by construction. And so I can compute CB and KB as usual, again for H equal to zero, and you get epsilon divided by KBT squared, and here you have la secante iperbolica, which is 1 divided by cos hyperbolic cosine squared, KBT. So this is what you get for the heat capacity per particle. And if you make a plot of this quantity, you see that CB divided by AKB as a function of temperature has a smooth behavior like this one. So for t going to zero is approaching zero here, because we have an exponential, effectively we have an exponential suppression provided in this formula, whereas for t going to infinity I have 1 divided by t squared. So here it's a smooth behavior. of CD, and indeed there's again to confirm that there is no phase transition. Okay, no phase transition. Indeed, in the Ising model, two-dimensional, that we will see afterwards, we will see that actually the heat capacity in the presence of a phase transition could have some problem. Actually, in the case we are going to study, there will be a jump. In some other models or some other situation can have a singularity. It depends on the models you're studying. So I think that this closes the discussion about the one-dimensionalism model. There's no much to say because apart from having a very nice analytical solution, it does not have. It has a let's say a paramagnetic behavior. Okay, so now you have an example of the diamagnetic behavior, which is the case of Landau diamagnetism. Now we have a case of paramagnetism, which is, for instance, the one-dimensional Ising model. Now we go on and do the Ising model in higher dimension. Now, the fact that the presence or absence of phase transition depends on the dimensionality, this was somehow already found in the case of the Bose-Einstein condensation, if you remember, because at some point we said that the Bose-Einstein condensation occurs for 3 dimensions. Okay, if you go to 1 dimension, if you go to 2 dimensions, it does not occur anymore. So the dimensionality of the system and the presence of critical phenomena or phase transition are strictly connected. Now, so what we do next is to do the Ising model for larger dimension. So for d larger or equal than 2, but actually, let me put here, we will do a mean field calculation. Mean field calculation allows to find a simple solution to this problem, which, however, is only well, maybe I would say it's not even qualitatively correct in the sense that, for instance, the presence of some singularities are not obtained in the mean field. But it is anyway useful because it allows you to understand more or less which is the physics that appears. But for studying, especially for studying phase transition, the mean field is actually, let's say, is an approximation, and we know from the beginning that we will have results that are wrong, basically, okay? And this by definition, because mean field means that we will neglect fluctuations, as we will see in a moment, and at the critical temperature, the critical point, actually, fluctuations are very important indeed. So the only way to deal with, for instance, the Ising model in dimensions larger than 2, so now in the case of 2 dimension, actually the problem can be solved exactly, and this is the Onsager solution. There is a full chapter in Kerson-Wang that you can read if you want it. It's one chapter just on that. It's a very complicated calculation, and the solution is exact. Okay, this is the only case in which we can find an analytical solution. Or you can even treat problems even in higher dimensionality by using a technique which is the renormalization group technique, that of course we will not have the time to do. This was actually, I think it was one of the topic of the course on critical phenomena.
So we will do a mean field calculation that will anyway provide us some insight into what's going on when you have a critical phenomenon. Okay. So the next topic is the following. Okay. So the starting point is again the same in the sense I have energy, eigenvalue if you want of the Hamiltonian, which is minus epsilon. Here you have again the sum over the Sj. Now I cannot put any more sk plus 1 because it's not a linear Ising model, it is at least two-dimensional Ising model. Therefore, I have two indexes here, I and j, which corresponds to the fact that you can couple. So let's make an example with two dimension. You can couple a spin with neighbors in all the directions in principle. Okay, so you need to consider the interaction of this guy, for instance, with this, and this, which are the first neighbors. And if you want to go to a second order, then you can also include those other four guys, and then you can go on. Okay, actually, in the renormalization group, you actually write down a general interaction model in which you interact with the first, then the second, the third, and go on. Okay. But anyway, so in general, you have a coupling for a fixed value of I, so the spin of I is coupled to the spin of j, and we put here a sum on ij, where this symbol means that we have to do a sum over the closest neighbors. Questo lo scriverò malissimo, neighbors vicini, sono dire vicini perché mi dimenticherò le H sicuramente. Vabbè, primi vicini. Oh, okay, let's put it this way, the closest spins. Okay. Yeah, so this, for instance, if I have a square, so in two dimensions, and I have a square, a lattice. So for lattice, I take a square in two dimensions. I will have four of them. Okay. Okay, so this is the interaction, the mutual interaction between spin, and then of course there is the simple term, which is minus h, which is the coupling with the external field, which is minus h, the sum over k, 1 to n of sk. Now, of course, the complicated part here is this one. Okay, so this is the same as before, and this is the complicated part because it contains a sum which can be as complicated as you want, depending on how many closest spins you consider in your system. Okay, and so let me make some note. So we call it gamma. We call it gamma, or we call it Q. Okay, no, I will introduce it later. I primi civi sono Q, va bene. Okay, I will do it later. Okay, then the magnetization is again, as before, by definition, is the ensemble average of Sk from K1 to N. This as before. It's just a Hamiltonian now, that is different. And you can actually define m, small m, as the ratio between m and the number of particles. Okay? So this is the magnetization of the particle. Which of course can be interpreted as the average magnetization of a particle. Okay, so now the difficult part, of course, is the coupling between the spin. So this is difficult. Okay. Now, if you are brave enough, you can read the solution in the case of two dimension in the book of Carson-Wang. We will do now this mean field approximation. This mean field approximation, basically, it's about fluctuation, the role of fluctuation. So suppose that I have SI, I can write SI as the ensemble average of SI. And what is the ensemble average of SI? It's just M. Okay. So this is equal to M. Plus, here I have the fluctuations that we will indicate just with the delta SI. The fluctuations consider the possibility of having, well, the fact that the spin I deviates from the average spin per particle. Okay. Now, if I do the product of two of those guys, Si and Sj, when I do Si and Sj, this will be an average Si plus delta Si times Sj plus delta Sj, which will be equal, almost equal to Si average, Sj average, product of this times this, plus Si average times the fluctuation delta Sj plus Sj fluctuation of Si. And here I put almost equal because I'm neglecting the second order fluctuations. Okay? Neglecting delta Si times delta Sj. Now this is equal to SISJ plus here I have SI times the fluctuation delta Sj, which is Sj average, sorry, is Sj minus the average Sj. And similarly, plus, then I have Sj times the fluctuation of Si, which is Si, minus the average Si. Now, if I do the calculations, I will see that one of those goes away, SISJ and SISJ goes away. Then I will have an average of Si times Sj, average Sj times Si, and a double product. So I have Si Sj plus Sj Si minus one is left in the product, so Si and Sj. Okay. Now, okay, so this was actually the product Si, Sj, which appears in the sum, okay? It's almost equal to this quantity. Now, let's do the following. I do not expect SI and SJ to be different. This at the end is an average. So then actually both of them are equal to M because of the system is somehow has translational imbalance. There's no reason for which the spin in the I position should have a different average with respect to the spin in the J position. Okay? And so this M is M squared. Therefore, this SI SJ is almost equal to MSJ and that multiplies SI plus SJ minus M squared, which is M squared. Okay. So now the mean field Hamiltonian has the following form. So the energy or Hamiltonian, but here we put mean field. Now it has the terms that has the usual terms minus h sum over k 1 to n of sk, which is the same as before. And here we have a minus epsilon. Then I have the product Si Sj that has indeed a coupling epsilon, but here I can collect a factor of n here outside. And then I have the sum over the spirits that I will work out in a moment. And I have Si Sj, Si plus Sj minus m. Okay. Equal, now this is the same. This is a minus epsilon m sum of ij. I will come now in a moment to the sum. Now here, somehow the sum is saturated over I and j, so the fact that here we have a Si and Sa is completely in the, so it's a double counting, you know? So here you have the sum over ij of Si, and here you have the sum of ij of Sj, which are both separated. Therefore, we get a factor of 2. So actually, we have a 2 Si minus m. Okay, just because of saturation of these indexes. It's not important if a sum on the pairs by taking Si or Sj. And now here comes the interesting point, the new interesting point. When doing the sum ij of 2 Si, I should consider what is this quantity now. And this quantity basically says that suppose that I fix, I'm fixing the index I, and then I'm summing over all the closest spins. And suppose that I have two different closest spin, and therefore this sum will be epsilon m, l'ho messo là. Okay. Okay. So first, let's call Q the number of closest spin. First of all, so this guy here will have is basically itself multiplied by Q, because actually when I fix I, so for say for fixed I have Q interactions with the closest spins. So actually this is degenerate in the sense that it's just the sum is Q times Si, and then I have to sum over Si. And then this is equal to the sum over I from 1 to n over 2si times q, which is the number of the closest spins, but I have to divide by a factor of 1/2. That comes from the to avoid double counting. I will explain in a moment. In the sense that here I have a sum over dispersed ij of si. I could have written sj, of course. So here, when I consider the pairs, I just need to take into account the interaction of two spin only once. Okay, and therefore I have to correct with this 1/2. Okay, so with all of this, now I can write the Hamiltonian in field, or the energy in field, in the following way. So we have minus h times the sum from k to n of sk, which is the usual tab, che usiamo 10 minuti. And then, okay, the difficult part was the interaction, the mutual interaction between the spins, which has a factor of m q epsilon divided by 2, where m comes from the midfield, the approximation, q and epsilon is the coupling, q divided by 2 derives from this sum, okay? Sum over pairs without double counting, okay? Q is the number of the closest spins. And this is multiplied by what? By by the sum of k 1 n of what was left 2sk minus n. Okay, so actually here, what I have to include m also. Okay, because also m was included in this sum. Okay, but it's the same. It is just constant. Yeah, so this is the mean field. Let me write it in a slightly different way. So the energy mean field is equal to epsilon q m squared n divided by 2. Where does this come from? Come from the sum over m. M is constant, and therefore I have m squared q epsilon 2 times n, because I have n terms. Okay, so it's with a plus actually, because it's a minus minus, and so I have a plus epsilon q m squared n divided by 2 minus. Here you see that the interaction with the external field and what is left from the mutual interaction are the same, apart from some constant. So I have the sum from 1 to n of sk. So I can collect the terms having these two terms in a unique term, which is which has a prefactor, which is h plus m q epsilon and q. And here you have the sum from k1 to n of sk. Now this is the mean field energy. So that has this term, which is quadratic in the magnetization of the single spin. And then we have this correction times this sum here. So if you want, it's a sort of, apart from this term, it's like having a pairing, a coupling, sorry, between the spins with an external magnetic field, which is an effective magnetic field, which is the real magnetic field plus epsilon and q. So we call this effective age. Okay, because the structure is actually the one of total sum times certain quantity, which I can interpret as a sort of effective magnetic field. Now I will have to compute the partition function. I will stop this, and then we go on next time. We continue next time. So the canonical partition function in mean field, okay, in mean field approximation, is a sum S1 Sn of, now I have to do e to the minus beta, and I have introduced these two terms in the Hamiltonian, the energy, in field energy. One of them was epsilon q m squared n divided by 2. And then I have an exponential of minus beta h, which becomes beta h effective. And here I have the sum of the speed, so k1 to n of sk. And that's it. Good. Now you see that this formula is actually very simple in the sense this I can put outside. So this is the exponential of minus beta epsilon q m squared n divided by 2. And here this exponential actually is e beta h effective S1, e beta h effective S2, and so on and so forth. So there is no real coupling now between the spins. I can sum separately all of these exponentials. So the first sum, the sum over S1 will influence only this term. The sum over S2 is always touches only this term, and so on and so forth. And when I do the sum, for instance, on S1 of a or exponential of beta h effective S1, what do I get? I get e beta h effective plus e minus beta h effective, which is a 2 cos h of beta h effective. Because considering the two values of S1, the two spins. So at the end, I will get a factor of 2 cos hyperbolic cosine of beta h effective to the power of n, because I have n of these terms. So I have 2 cos h of beta h effective to the power of n. Okay, let me write it now. This is z of c. Okay, so it has this exponential factor, and then there is 2 cosine, hyperbolic cosine of beta h effective to the power of n. This is the canonical partition function. Aspettate un attimo, dov'è che stiamo? Siamo 1 a 2, la canonica l'abbiamo calcolata. Okay, now from the canonical, of course, you can compute, for instance, the free energy per particle, or the free energy, Helmholtz free energy. A is minus kb t log of zeta dc, which in this case is a minus kbt. Then I have the first exponential provides a contribution which is minus beta and epsilon q squared, m squared q divided by 2, meno beta n epsilon qm 2, sì, plus n, and then I have the log of 2 hyperbolic cosine of beta And here you have the H effective, which is H plus epsilon and Q. Okay. Now this is the Helmholtz free energy, and we can also compute. Remember that the magnetization was the minus derivative of A with respect to H, and the magnetization per particle at this point is minus derivative with respect to H of A to N. So I can, and the figure will stop here, I can derive this, I can divide by n, so of course I have n here and n here. I can derive with respect to h, and let me see, where is the h? H is only there, okay? So the magnetization of a particle, it has actually a very simple formula. I just need to do this derivative. N goes away, the kBt is still there, but I have the denominator, I have 2 cos hyperbolic of beta times h plus epsilon and q. 2 coseno, sì. Then I have here, I have 2 derivative of cosinus, sinus, hyperbolic sinus of beta h plus epsilon and q. And then I have an additional factor of beta because I'm deriving with respect to h. And then I think I have another 1 over beta there. Yeah, and I think that's it. And the minus, I have a minus here. Okay, maybe I close here. I will continue next time from this. Okay, but I will repeat these calculations. But the magnetization, if you want to look at it, is basically provided by this formula. M is the tangent, hyperbolic tangent of beta. And here I have h plus m epsilon q, which is a nice formula in the sense that you see here that m appears here and here. It's a nonlinear equation. And actually the trick to have a phase transition is to have really such kind of nonlinear equations. So those nonlinear equations indeed have solutions which are not trivial, as we will see next time. E smetto qua perché è già l'una, altrimenti Luciano mi ammazza. Ci vediamo martedì.
Arrivederci a martedì.
Martedì facciamo lezione, quindi? Anche se
no, martedì non c'è lezione, è vero, ci vediamo giovedì. No, martedì non c'è lezione. Ok, grazie.
Arrivederci, grazie.
Ciao.
Arrivederci.
Arrivederci.